Now we will be talking about the energy band in a semiconductor. So first we will going to talk about the energy band diagram of a germanium. Okay, so as we have already defined that germanium is a semiconductor device, and germanium has got a 4 valence electron in their last orbit. So we are talking about this orbit configuration. So you can see that germanium has got the 2e, 8e, 18e and 4e. So we will be drawing the energy band diagram on this basis. Okay. So I will be writing the 2 electrons in the first band, then 8 electron in the second band, then 18 electron in the third band, and 4 electron. Okay, is the outermost band, or we can say it as a valence band. This is known as the first band. Electrons. This is known as the second band. 18 electrons in the third band, and last band, which is known as the valence band. Okay, so in a valence band, we have got a 4 electrons. Okay. Now we will be plotting the energy band diagram. Okay, so we will be writing the band energy, and it has been given in the electron volts. And since we are drawing it for the germanium, so I will be writing germanium here. So the lower band, starting from the second band, so we are saying the lower band is our second band, then we have got third band, and then we have got valence band, and then we have got the conduction band. Okay, and this I'm highlighting with the yellow color. So this one I'm writing at it as a conduction band. And we have already defined that semiconductor is a device which has got a very small gap between this valence band and the conduction band. Therefore, when we are talking about the energy band between the valence band and the conduction band, we have got zero point 0.7 electron volt for germanium. Okay, and this I'm drawing with the green, so this is my valence band. So here we can say that the small energy is needed by the valence electrons to cross over the conduction band, and we can say that even at the room temperature some of the valence electrons may acquire sufficient energy and they may jump from the valence band to the conduction band. So now we will going to look at the silicon. So from the previous slide, we have seen that silicon has got the 2 electrons in the first orbit, 8 electron in the second orbit, and the fourth electron in the valence band. So I'm writing 2 electrons in the first band, 8 electrons in the second band, and 4 electron in the valence band. And now we will going to draw the energy band diagram. So here I'm plotting again the graph of silicon with respect to the band energy that has been given in the electron volt. So I'm writing band energy and it is given in the electron volt. Okay, so in germanium we have not drawn the first band, but since we have less orbit in the silicon, so we can draw the first band here. So I'm writing this as a first band, then we are drawing the second band, then we are drawing the valence band, and then we are drawing the conduction band. So let me write it: first band, second band, valence band, and the last one is the conduction band. So I'm doing the green color in the valence band. Okay, so this is my valence band, and the last one is my conduction band. So I'm drawing the it with the yellow color. So this is my conduction band. And we can say that the energy between the valence band and the conduction band. So we have got a 1.1 electron volt energy gap between the valence band and the conduction band. So we have to make a note that even at the room temperature, as we have explained in the previous slide for the germanium, so same thing is for the silicon, that even at the room temperature, we can say that some of the valence electron may acquire sufficient energy. Okay, so I'm writing it. Some of the electrons, valence electrons. Okay, I'm underlying this valence electron because it is, we are talking with respect to the valence electrons. Okay, so some of the valence electron may acquires, I'm writing with the different colors, sufficient amount of energy. Okay, because the energy gap between the valence band and the conduction band is very small. Okay, so even a small amount of energy can help your valence electrons to jump from the valence band to the conduction band. And these electrons become a free electrons. Okay, so that is important. We are writing that these electrons becomes a free electrons. That means the electrons that has entered into the conduction band are your free electrons. So we have to make a one note here is that number of free electrons available at this room temperature is very small. Okay, so we can make a note here is that at room temperature, silicon and germanium is neither a good conductor nor an good insulator. Okay, so I'm writing at room temperature, silicon or germanium is neither a good conductor nor an insulator, and therefore these substances are called as semiconductor. And this is the reason why we are calling them as a semiconductor, because we cannot define the it as a good conductor or a good insulator.